The next topic that we're gonna discuss is about the interpretation of partial derivative. Like I taught you earlier, when you like to differentiate with respect to x, you're gonna fix y. And when you like to differentiate with respect to y, in this case, you're gonna fix x. So the way that we're gonna interpret the meaning for the partial derivative will be in the way that you have a surface z equal to fxy, and in this case, it's gonna be the surface z equal to 4 minus x squared minus 2y squared, and you're gonna fix one variable. So let's say example, you have fix y equal to 1. So this one, you have y equal to constant 1. Okay, y is a constant, and in this case, you have y is a constant 1. And the thing that you see that you have the surface, the gray surface like this one, and you have the plane y equal to 1. So this one will give you the plane. And when you have the surface and the plane, you're gonna have the cross section. So you have the surface, you have the plane. The thing that you can see is gonna be, you're gonna have the cross section of the surface and the plane. And this guy turned out to be a curve C1. Okay, so you see the trace here gives you the curve C1. Okay, so my C1 is this guy. And if you find the partial derivative at the point 1, 1, the thing that you would get turn out to be the slope of the tangent line. So this one, I'm gonna say that this guy is a cross-section curve. Okay, so you have the cross-section curve and you have the plane, which is fixed y equal to 1. And this line is the tangent line. And when you have the tangent line, the thing that we have in calculus 1 is going to be you have to be able to find the slope of this tangent line. It's going to be the tangent line, and the slope will turn out to be the partial derivative at x equal to 1 with slope equal to the df dx at x equal to 1. Okay, so that is going to be the meaning for this tangent line, and it's going to be the meaning of the partial derivative with respect to x at the point 1, 1. Similarly, if you like to find the partial derivative with respect to y at the point 1, 1, the thing that you are having is going to be, you're going to have the plane x equal to 1. Okay, so this one is going to be the plane x equal to 1, and you have the cross-section curve C2, okay, and your C2 is this curve. And you also have the tangent line. Okay, so let me use other color. It's gonna be easier to see. So this one, I use the blue color. And you have the tangent line. So this one will be the tangent line. Okay, so you have the tangent line, and the slope of the tangent line turn out to be df dy at 1, 1. Okay, so it's going to be with slope okay, so with slope df dy at 1, 1. Okay, so it's going to be that meaning. So this one, you see the difference between df dx and df dy is going to be different cross section, and when you differentiate with respect to x, y constant, so you're going to have the plane y equal to 1 for the cross section, and you're going to have the plane x equal to 1 for the cross section when we are discussing df dy. Okay, let's try to find the slope for me here. So you see that you have z equal to 4 minus x squared minus 2y squared. Okay, so this one is my surface. And you have dz dx, okay, so you have dz dx equal to 2x, and you have dz dx at 1, 1 equal to negative 2. So you have the slope equal to negative 2 for this tangent line to the curve C1 at 1, 1. And you have the slope of the tangent line. So you have dz dy equal to 4y, and you're going to plug in x equal to 1, y equal to 1 into that derivative. So it's going to be negative 4. So you see that this guy will be equal to negative 4 for df dy at 1, 1. Okay, so that is going to be the slope of the tangent line. So the thing that we're going to do next is going to be, I'm going to conclude that when you have the partial derivative with respect to x at AB, it means that it's going to be the tangent, the slope of the tangent line to the curve, which is the intersection of the plane y equal to b and your surface z equal to fxy. Okay, so if you like to see the picture, you can see from this example. And if you have the partial derivative with respect to y, that means you are studying the change in y when you fix x equal to a, and you gonna get the slope of the tangent line. Okay, so you get the slope of the tangent line to the curve, which is the cross section, or the intersection between the plane x equal to a and z equal to fxy. So for this one, we like to find the slope of the tangent line to the curve in which the yz plane. So you have three-dimensional. So you have x, y, and z. And the yz plane is this plane. Okay, so it's going to be this plane. Okay, so it's going to be this plane. And it's going to be the plane x equal to 0. So this one is the plane x equal to 0. Okay, so it's going to be the plane x equal to 0 on that wall. And you have the surface z equal to arctan y e to the 2x. So what does it mean? It means that you're gonna have the curve. Okay, so the pink curve, okay, so it's gonna be this curve. I can not use the pink one. The pink one represent the plane. So this one is gonna be the curve. Okay, so this one is the curve C, which is the intersection between surface and what is called and the plane. Okay, so this one is the curve C, which is the intersection between. Okay, so it's cross section of the surface z equal to arctan, okay, y e to the 2x, and the plane x equal to 0. How could we obtain C? So in this case, C will turn out to be z equal to arctan, okay? And you're gonna plug in x equal to 0 into the equation. So it's gonna be x equal to 0. So it's gonna be y e to the 2 times 0. So this one is going to be just z equal to arc tan y. Okay, so you have z equal to arc tan y, and you would just like to find the derivative at the point 0, 1 pi over 4. Okay, so it's going to be this point. Let me draw the curve here. So it's going to be 0, 1, and we like to have the tangent line. Let me use something darker. So for this one, it's going to be the tangent line. Okay, so it's going to be the tangent line at 0. Okay, so this point is 0, 1 pi over 4. Okay, so this will be just the point that you have here. Okay. So the point is here. Okay, so the point is here, which is the tangent point that there. And you're gonna see that you have z equal to arc tan y. The thing that you would do is gonna be you're gonna just find derivative with respect to y, okay, in order to find the slope be diff, right? So it's gonna be dz dy, so it's gonna be 1 over 1 plus y square. Okay, and you have the slope would be just the z dy at the point 0, 1 pi over 4, and this guy turned out to be just 1 over 1 plus 1 square equal to 1/2. Okay, so that is going to be this slope. Okay, so the slope turned out to be equal to 1/2 in this case. The second one, okay, for the second one, you have the plane y equal to -1 intersect the surface 4x squared minus 3y squared plus z equal to 5, and you like to find the slope of the tangent line at the point 1, -1, 4. Okay, I'm not gonna sketch anything. I'm gonna just find the curve C. Okay, so the curve turned out to be you just put y equal to -1 into your surface. Okay, so you're gonna just put y equal to -1 into this surface. We're gonna just use yellow guy. So you have y. So the curve turned out to be just 4x squared minus 3 times -1 square, okay, plus z equal to 5. And you're gonna solve for z. Okay, so z in this case will be equal to 8 minus 4x squared. Okay, so it's going to be 8 minus 4x squared. Okay, so you move to the other side. And then what? And then you're gonna find dz dx. How would I know that it's going to be dx? Because you don't have y anymore. So it's going to be dz dx, and it's going to be -8x. Okay, and for this one, you gonna just have the slope equal to dz dx at 1, -1, 4. So it's gonna be -8 times 1. So it's gonna be -8. Okay, so the slope in this case turned out to be equal to -8. Okay, so that the second example for us. So after we know how to find these two tangent line, okay, so if you like to find the tangent line, you'll be able to find the tangent line by just using like the line that we have at the beginning of chapter 13. So after you find these two tangent lines, you see that you'll be able to find the tangent line T1 and the tangent line T2. and you be able also to find the thing that's gonna be the tangent plane. I taught you before that when you have a surface, okay, so when you have a surface like this one, and if you want to touch the surface, if you want to touch the surface by using a line, you're gonna be able to touch this surface like an infinitely many way. So it's not gonna be unique tangent line for the surface. However, if you like to touch the surface by a plane, okay, so if you touch the surface by a plane at the point, so let me use my mouse like this, okay, so you see the mouse, and if I like to touch the surface like this, so if you have the surface and you see that if I like to touch at this point, okay, so if you like to touch at this point, it's going to turn out to be moving around, okay. However, if you like to touch this surface by just a plane, okay, so let me use my card like this one as a plane. So you see that when you touch this guy with a plane, it's going to be unique plane, and this guy will be called tangent plane. Okay, so this guy will be called tangent plane. And if you want to find this tangent plane, the way to obtain the tangent plane will be you just have the point x0, y0, z0. Okay, so you just have the point x0, y0, z0, x0, y0, z0, the point x0, y0, z0. Okay, so that is going to be not quite clear much. So let me use red color instead. So you use red guy and you have x0, y0, z0. So for this point x0, y0, z0, we're gonna have the tangent plane given by, you see, it's gonna be z minus z0, and you have the derivative. Okay, so this one is gonna be the change or the slope for x. Okay, so the slope for x multiply with x minus x0, and you have the slope for y, y minus y0. If you compare with Cal 1, your calculus 1 will be given in the form of y minus y0, and you have the slope equal to the derivative at x0 times x minus x0. So for calculus 1, you have this slope m. Okay, so you have this slope m. And for calculus 2, you have to take care the slope given by two values, the slope with respect to x and the slope with respect to y. Okay, so you have two slopes, and when you multiply the slope with respect to x with x minus x0, and you multiply the slope with respect to y minus y0, this one will give you the slope for each component. So you have x component and you have y component, and this one will give you the equation of the tangent plane. This is just how to memorize the meaning of everything. However, the way to discover this one is kind of difficult a little bit in order to find the normal vector. So if you recall that this one, you're gonna have the tangent vector, okay, one vector, and you have another vector, and you're gonna have the normal vector turn out to be the vector that perpendicular to this T1 and T2. Okay, so you're gonna have to find the cross product or something like that. That is gonna be kind of the proof for this formula. However, we're gonna just recognize the formula using calculus 1, and we're gonna use this formula in order to find an equation of the tangent plane. Okay, so we're gonna find an equation of the tangent plane to the falling surface at the given point. So for number 1, you're gonna have z equal to x squared plus y squared, and the point turned out to be 2, -1, and 5. So this one will be your x0, y0, and z0. So the thing that you will need, you need derivative. Okay, so you will need dz dx at 2 negative 1, and you will need dz dy at 2 negative 1. Okay, so you will need these two partial derivatives. So for dz dx, you're going to begin differentiating. Okay, so you have dz dx equal to 2x, and you have dz dy equal to 2y. Okay, so that will be my partial derivative. And so you have dz dx at 2 negative 1 equal to 2 times 2 equal to 4. And you have dz dy at 2 negative 1 equal to 2 times negative 1 equal to negative 2. Okay, so you have this one turn out to be the purple guy, and this one turn out to be the yellow guy that you just gonna put into the formula in the box up there. Okay, so you see that this one is the purple one that you're gonna put here, and this one is negative 2 that you're gonna put here, and you see that you're gonna just put x0 equal to 2, y0 equal to negative 1, and z0 equal to 5 into the equation of the surface. So this will allow you to have z minus 5 equal to negative, not negative, 4x minus 2 minus 2. So it's going to be minus 2x, not x, y plus 1. Okay, so for this one, you have negative 2, which is the yellow one, and the purple one. Okay, so you see that it's going to be just plugging in x0, y0, and z0, and this one will give you the tangent plane. Okay, so that will be our final answer. I will let you to do number 2 on your own. Okay, so you need the purple one and you need the yellow one in order to obtain the tangent plane. Okay, and after we have the tangent plane, the thing that we can use tangent plane to do is going to be about approximation. So when you like to find the approximation like this, okay, so let me give you one example first. If you like to find the approximation for this number, normally you're gonna just say that, hey, use calculator, and the algorithm that the calculator used turned out to be the total differential, or some calculator use the Taylor series or something. For this one, okay, the algorithm that we can have is going to be just, we can just use the differential in order to give us the approximation for something like this. The way or the idea turned out to be, so you see that if you like to find the approximation for this value, which is complicated, okay, so this one is the point on the surface that kind of complicated to compute. And the thing that you know is going to be, you're going to have the next point that close to this point. Okay, so you have the point AB that close to this point, and you'll be able to compute the tangent plane. Okay, so for this one, you get the tangent plane. So you have the tangent plane down here, and if you want to know the value here, okay, you're gonna instead use the point on the tangent plane for the approximation. Okay, so we're gonna use the tangent plane and we're gonna use the point on the tangent plane in order to obtain the approximation for us. So you see the tangent plane here, okay? You have the purple one and you have the yellow one here, okay? And you have Z. And you like to know the point, okay? So you like to know the value of Z when X equal to A plus delta X, okay? So you like to know if A plus delta X. So this one is gonna be the tangent plane. So you put, okay, so you put Z equal to F A plus delta X B plus delta Y. Okay, so you put Z equal to this guy and you put X equal to A plus delta X and you have y equal to b plus delta y. The thing that you will get will be, you will get f a plus delta x, b plus delta y turned out to be, okay, turned out to be, so you're gonna put this one into the equation of the plane. So it's gonna be FAB, right? And this one turned out to be FX. I need more space. So it's going to be fx at AB and you plus A plus delta x, okay? And you have minus A and A plus delta x minus A and you have Fy at AB and you have B plus delta y minus B. And this one is the purple one and the yellow one respectively. Okay, so for this one, I'm gonna be able to simplify this one. So this one will be the approximation. Okay, so the approximation for f a plus delta x b plus delta y. Okay, so this one will be the approximation equal to fab. Okay, so this one is the approximation because normally you have this one is gonna be on the plane, so it's turned out to be this set. Okay, it's not equal to this one, this point. Okay, I gonna point this one. So you like to know this guy, right? However, the thing that we have for this point turned out to be this point. So you see that this one is not the exact value. It's gonna turn out to be approximation. Let me just use set here. Okay, let me just use set here. I'm not putting. So it's gonna be this guy. Okay, set, and you gonna. It's going to be confusing a little bit. Let's just use set tutor. Let's just use set tutor. Here it's going to be set tutor. So you see that the set tutor will be on the surface and you have this guy is about set tutor for the approximation, and for set tutor, what is set tutor? Let's highlight set tutor. What is set tutor? So you see that set tutor here turned out to be, you move this guy to the other side. So turn out to be equal to FAB, okay? And you're gonna add by this term, okay? So it's gonna be, so it's gonna be these two guys that I would just copy them down. Okay, so that is gonna be just how we get the approximation. I show you one example to see what's going on. And by the way, we can simplify. Okay, so let's simplify this one a little bit. I shouldn't copy. So you see that this guy can be just simplified to delta x. Okay, and you have this term up here. And for this guy, it's gonna be delta y. And that's it. Okay, so let's try this example. We like to approximate, okay? So we like to approximate square root of 3.05 square, okay, minus 1.97 to the third power. So for this one, the first step, we're gonna have fxy, okay? So we're gonna have our surface. Our surface turned out to be, you see the structure of the function. You're gonna change number into x and y, okay? And the function that you would get will be square root of x squared minus y to the third. So you have fxy equal to x squared minus y to the third inside square root. So this one will be the surface. And you need, okay, f at 3.05 and you have 1.97. Okay, so you need the approximation of 3.05, 1.97. So what should we do? The thing that we're gonna do will be, we're gonna write this one as f3 plus 0.05 and 1.97 come from 2 minus 0.03 or 2 plus negative 0.03. So this guy will be your x and y, okay? So you're gonna have 3 plus delta x and negative 2 plus delta y, okay? So in this case, you're gonna just have f 3.0 3 point delta x, 2 point delta y. So we're gonna find the tangent plane, okay? So we're gonna find the tangent plane phi. So this guy will be your A and your B in the formula that we just derived, okay? So we're gonna find the tangent plane at 3, 2. Okay, so we're gonna just find the tangent plane at 3, 2. So we need, okay, so we need f 3, 2 will be our z0. So in this case, it's gonna be what? Square root 3 squared minus 2 to the third. So it's gonna be root 1 and root 1 equal to 1. And this guy is your x0, y0, okay? So we're gonna have z minus z0 equal to fx x0, y0, and you're gonna have x minus x0, plus fy x0, y0, y minus y0. So this one is the yellow one and the purple one. Okay, so that is going to be the thing that we're gonna find next. So we need fx and fy. Fx. So you differentiate with respect to x. Okay, let me use other color. So for this one, you're gonna have derivative with respect to x. So this guy will be what? This guy will be just 1 over 2 root x squared minus y to the third, and you find derivative with respect to x of x squared minus y to the third. So it's going to be 1 over 2 root x squared minus y to the third. Okay, and you differentiate, you get 2x. Okay, so that is going to be fx, and you have fy is going to be 1 over 2 root x squared minus y to the third, and you have the dy of x squared minus y to the third. So you get 1 over 2 root x squared minus y to the third multiplied with 3y squared. So it's gonna be it. And then you need the purple one. So you have fx at 3, 2, right? Fx at 3, 2. So it's going to be 2 times 3 over 2. So square root 3 square minus 2 to the third. So it's going to be equal to 3. And you need fy at 3, 2. So it's going to be negative 3 times y squared. So it's going to be 2 squared over 2. So square root 3 squared minus 2 to the third. So in this case, it's going to be negative 6, right? So it's going to be negative 6 because I have negative 12 over 2. Okay, so it's going to be just that. And then what? This one will give you the purple guy. Okay, so this one will give you the purple guy, and you get the yellow guy that you would just plug them in. So you're gonna have the tangent plane. Okay, so the tangent plane will be, the tangent plane is, okay, the tangent plane is, I forgot the tangent plane is, so you get z minus z0, z0 equal to 1. So you have z minus 1 equal to 3x minus what? X minus 3, okay? And you have negative 6, y minus 2, y minus 2. So for this one is the yellow one and the purple one. Okay, so this one will be the tangent plane. Okay, so you're gonna have z tilde. Okay, so in this case, you're gonna have z tilde equal to 1 plus 3x minus 3 minus 6y minus 2. Okay, and so this one is your tangent plane, and you like to find the approximation, right? So you need f 3.05, 1.97. So this one is f of 3 plus 0.05 and 2 minus 0.03. So for this one, it's going to be this color. And for this one, you have delta x, delta y. Okay, so you have delta x, delta y. So you basically use, okay, set tilde. Okay, so you use set tilde. So you basically put 3.05 into x and 2 minus 0.03 into y, basically. So it's going to be 1 plus what? 3, and you have 3.05 minus 3 minus 6, 1.97 minus 2, okay, minus 2. And this one will be just 1 plus 3 times 0.05 minus 6 times, so it's going to be 6, and this one will be 0.03. So it's going to be 1 plus, so it's going to be 0.15, okay? And I forgot negative sign, so it's going to be 0.03, so it's going to be plus 0.18, so it's going to be 1.33, okay? So it's going to be 1.33, and it will be the approximation that we are looking for. Okay, so don't forget that this guy is the same as the one that is in the question, 1.97 to the third. Okay, so this will be just the square root. Okay. Okay, so let me conclude what I did. It's gonna consist of 3 steps. The first one is you are asking for the tangent plane. Okay, so you are asking for the tangent plane. So the first step turn out to be the green guy. Okay, so this one will be your first step. And your second step will be when you have the tangent plane. Okay, so you have the tangent plane. And the third step will be your approximation. Okay, so it's going to be first step, second step, third step. And maybe we have some small step for 0 step here. The 0 step come from when you have to define the function. Okay, so when you have to define the function by seeing the structure. So for this question, it's going to consist about 4 steps. So you first define the function, you identify the point x0, y0, you find the tangent plane, okay, at that point, and you're going to use that tangent plane in order to obtain the approximation. Okay, let's do one more example. You have fxy equal to y squared over 1 plus sine x to the y at 0, 2. We like to find the tangent plane and use it to approximate f0.03, 1.98. So the meaning of linear approximation, okay, so the meaning of linear approximation, this one is just tangent plane. Okay, so tangent plane has another name, the linear approximation. So we just like to find the tangent plane at 0, 2. Find tangent plane at 0, 2. So you see this one, okay? So you see this one is going to be, you need tangent plane at 0, 2. Tangent plane at 0, 2. So for tangent plane at 0, 2, so you need fx 0, 2 equal to, and fy 0, 2 equal to. So this one is the yellow one and the purple one as before. Okay, so as before. And you gonna just have to find the first step. You're gonna differentiate with respect to x, differentiate with respect to y. Okay, so you find fx and fy, and then you find fx at 0, 2, and you find fy at 0, 2. Okay, I will let you do this one on your own first. I will give you some guideline, and you're gonna have the tangent plane. So you have the tangent plane will be, okay? And then the third step will be you need f at 0.03, 1.98. Okay, so this guy will be about that tilde that you gonna plug into the tangent plane. So when you have the tangent plane, it's gonna be, let me find that for you. So for tangent plane at 0, 2, so you're gonna have that 0 equal to f02. F02, here 0 will be your x0, your 2 will be your y0, okay? And z0 will be you just plug in y and x into the equation. So you get 4, right? So it's gonna be 4. So you're gonna have z minus 4 equal to x minus 0, and you have y minus 2, and we need the purple one and the yellow one into this number. So you have the purple one and you have the yellow one. Okay, so you need to find the purple one and the yellow one that you're gonna plug here, and you're gonna solve for that tilde equal to 4 plus, and you're gonna have the purple one times x. Okay, so you're gonna have the purple one times x, and you're gonna have the yellow one times y minus 2. Okay, so I give you some guideline like this, and I hope that you'll be able to fill the blank that I left you. Okay, everything turned out to be nice number. Okay, and then you gonna approximate by letting x equal to 0.03. So you're gonna plug in x equal to 0.03 and y equal to 1.98 into the tangent plane, and you'll be able to obtain the approximation that you're looking for. Okay, so please do this one on your own, and we're gonna cover this one during the recitation. And let's go back to example 17. For example 17, you have fxy equal to x squared plus 3x minus y squared. We like to find the differential dz. I didn't cover this one yet. Let's go to the definition of dz a little bit. This one, you have the dz turn out to be the form of the tangent plane. So you have the tangent plane z minus c equal to the purple one. Okay, so this one is the purple one times x minus a, and the yellow one times y minus b. In math, we can write this guy as dz. Okay, so it's going to be the difference in z. So it's going to be dz. And you have the purple guy, which is your fx. And you have x minus a here that can be written as dx. Okay, and you have the yellow guy. Okay, you have the yellow guy, and you gonna have y minus b, which can be just this dy. Okay, so you have dz equal to fx dx plus fy dy. This guy is called total differential. Okay, so this guy is called total differential, and this one can be used to give the approximation like I told you here already. So this one is the thing that I wrote down here, so I don't have to cover them again. So this one, the question asks you to find the, I forgot total, let's put total. So the total differential dz. So for dz, the formula will be given by, okay, so the formula will be given by fx dx. Okay, so it's going to be fx dx plus fy dy. So you would need fx and fy. Let's find them. So you're gonna just find derivative of x squared plus 3xy minus y squared. So this guy will be 2x, okay? So it's gonna be plus derivative of 3xy is gonna be with respect to x, so it's gonna be 3y and plus 0 minus 0. Okay, so it's going to be fx equal to 2x plus 3y minus 0. And you have fy, okay, so you're going to differentiate this guy. It's going to be 0 plus 3x, okay, minus 2y. So you have the purple one and you have the yellow one given in this form. So you're gonna have the z equal to 2x plus 3y dx plus 3x minus 2y dy, and this one will give you the thing called total differential. Okay, so this one will give you the total differential for number one. Okay, so this one is going to be number one. Okay, so the yellow one and the purple one. The second one will be when x changes from 2 to 2.05, y changes from 3 to not 3 to 2.96. We like to compare the value dz. Okay, so we like to compare the value dz and delta z. So what does it mean? It means that for delta z, okay, so for delta z, so you're gonna have x equal to 2 change to 2.05 and y equal to 3 change to 2.96. Okay, 2.05 is going to be just 2 plus 0.05 and 2.96 is 3 plus negative 0.04. So this one allow us to compute delta x and delta y respectively. Okay, so this is going to be the change in x and the change in y. Okay, so you have delta x and delta y, and you see that the value of z, so it's going to be f, so the point will be f 2, 3 will change to f 2.05 to 0.96. So delta z, okay, delta z will be just the difference between these two numbers. So it's going to be f 2.05 to 0.96 subtract by 2, 3. Okay, so it's going to be subtract by 2, 3. So the thing that you will need to compute, So you're gonna just plug in x equal to 2.05, y equal to 2.96. So it's going to be 2.05 square 3, 2.05, 2.96. Okay, minus 2.96 square. So this one is your first f, minus 2 square plus 3 times 2 times 3. Okay, minus 3 square. Okay, so you can expand this one out. So you have 2.05 times 2.05 and you calculate them. So everything here can be done by hand or you use your pocket calculator a little bit. You're gonna get 13.6499. Okay, so it's going to be a little bit difficult. Okay, so it's going to be messy in order to compute this number. And you're gonna subtract by this number, which is quite easy. So it's going to be 4. This guy will be 18. So it's going to be 22 minus 9. So it's going to be 13. So it's going to give us 13. So you see that delta Z is exactly equal to 0.6499. So this one is exact value. Okay, so this one is exact value. So you have delta Z, and delta Z turned out to be difficult or messy to compute for this first number. For the second number, okay, so we like to compute dz. Dz will be you gonna plug in x equal to 2, okay, so you're gonna have dz equal to this guy, okay. Let me just copy and let me erase this one. I'm gonna paste this guy and I'm gonna just change the color. So I have the z equal to 2x plus 3y dx and 3x minus 2y dy. Okay, so I'm gonna erase this guy. So you have this z equal to this, and you would just put x equal to 2, put x equal to 2, y equal to 3, and dx will be delta x, dy will be delta y into dz. Okay, so we gonna obtain, help me, so it's gonna be 2 times 2, 3 times 3, okay, dx will be delta x, so it's going to be 0.05. Okay, so this guy is 0.05. And delta y will be negative 0.04. Okay, so you would just have 3 times, what is going to be? 3 times 2 minus 2 times 3, and delta y is negative 0.04. Okay, so that will be the number that you should have. And you see that this one will be, you not need calculator, because this one is going to be 13 times 0.05. And for this guy, it's going to be 0 times negative 0.04. And you see that this guy will be 0.65. And as you can see, the exact value is equal to 0.6499. And this one is going to be 0.65. And this one turned out to be a good approximation. And we don't have any messy calculation. Okay, so you see that this one is kind of difficult to manipulate or difficult to expand it out. However, for using this dz or the total differential, the thing that you would get turned out to be kind of good approximation without any difficult calculation at all. Okay, so this is how we deal with the differential or the total differential dz, and it will give us the error in the value of z, very good approximation compared with the exact value. Okay, so I left you with this one that will be on your third exam. Okay, so you should be able to follow the step, and you can follow example 18 in order to complete this example and try to get the approximation for me. Okay, I will give you the solution a little bit, that the solution will be, okay, so let me write down the solution. The solution that you're going to get for final answer in this case is 3.68. Okay, so try to obtain that approximation form. Okay, so I'm going to leave you here today, and that is going to be all for the tangent plane. Okay, so we begin with the interpretation of fx and fy, and we have the tangent plane, and we use the tangent plane in order to do the thing that called linear approximation or the total differential. Okay, so that would be all for this clip.